scan the chat. Hear me okay? Wonderful, thanks. All right, how's everybody doing? Okay, so let's switch that over here. So as always, don't forget the seating survey, section 4, ILC 118. Upcoming deadlines, the only thing this week is homework 8 on Friday. The office hours tomorrow are canceled because I am sitting on a PhD dissertation defense committee during that same time. And so if anybody was really counting on speaking with me tomorrow, please contact me so that I can set up an individual appointment with you. Happy to do so. And as usual, the Sunday Piazza participation cutoff for week 10. The next week, we should be back to normal in terms of content videos and such. On exam 2, there's a Piazza post where the results have been posted and the curves that I've implemented for exams 1 and 2. I posted a walkthrough video on the exam last night. And my conclusion on the whole kinetics simulation spreadsheet is that while I really liked the idea, I think I should have done it as an activity instead of as an exam so that it would have been a less time-sensitive, less stressful kind of environment to do that sort of thing, and perhaps even have been able to do it as part of a group. So that is one of the reasons why I am perfectly fine with doing the curve on the exam that I did, and I'm not going to be doing something like that on any of the future exams. So that's where we are. So after the curve, this is what, if I plug absolutely everyone's grades into the grade projection spreadsheet, this is what we end up with in terms of projected course grades for the class. So roughly equally split between the A's, B's, and C's, and we will see how that goes moving forward. Okay, do we have any logistics questions before we get on to muddiest points? Okay, so for anyone that didn't tune in either Monday or Tuesday, those 2 days I did something that I typically don't do, which is I lectured on the content rather than using content videos, because I didn't have the content videos together. So both of those 2 class periods were identical to each other in large measure, covering the same material, and was the introduction to the material on it. So if you are still having trouble with any of the concepts from sort of an introduction to the concept standpoint, those would be good things to go in and pay attention to. Okay, so we have a bunch of questions that have come up on Piazza. The first one on PH and POH is something to just to think about and understand mathematically. Was calculating the concentration of hydroxide in a solution with this POH, and indeed the formula for calculating concentration of OH from the POH is 10 to the minus POH. And so that was what was entered, and it was counted right, but then the student was a bit confused about why the displayed answer was this instead of this. That is because this is the form of the same number, just written in standard scientific notation, where you're taking 10 to the integer value rather than to some decimal value. So just paying attention to that aspect of what scientific notation is versus raising 10 to anything is worthwhile. And you'll notice that in this case, we have something that is larger than 1 times 10 to the 9th. So we would expect it to be 10 to something larger than -9, which is in fact what we get. Okay, there was also a question to look at an example calculation for a weak base, and I'm happy to do that. So the thing to note here is that we are not told exactly what the base is. We have a KB for it, we have a solubility, and we have a molar mass. So we're trying to figure out what the pH is. What do you think the steps should be towards trying to solve this problem? Where should we go first? What we're trying to do is find the pH of a saturated, the pH of a saturated solution of this, this compound. Okay, the chat suggests you need to find molarity first. Okay, which piece of information here is going to tell us the molarity of the solution? The molar mass will give us the molarity. So that is going to be grams per mole of the pure substance. But what we're looking for is a saturated solution. So which piece of information is going to give us the concentration of the saturated solution? Yes. The molar mass and the solubility, right. So solubility is going to be the thing that tells us how much is in it, and we simply need to convert the grams to moles in order to find the concentration in molarity, which is moles per liter. So we have our 1.667 grams per liter, and we use our molar mass as a conversion factor. We want grams to cancel, so that goes in the denominator. And from that, we find our molarity. So 1.667 divided by 303.36 gives us 0.005495 molar. Okay. So now that we have this, we have the concentration of the weak base. What do we do to find the pH? Do the log of this? So we can do that to find sort of the P concentration of it. So, so we can do that. But is this the concentration of the hydronium ion, which is what pH is referring to? Nope. So maybe we ought to write down how a weak base acts and what it is that it does. If I were to write down the prototypical base reaction, if we call the base B, what would I write down? Yes. Yep, it's going to react with H2O. Now, from the Bronsted-Lowry definition, what is a base? Yeah? A proton acceptor, that's right. So a proton, remember, is an H+. So our product here is going to be BH+. And what does that leave from the water? Yeah. The hydroxide ion, right, OH-. So this is the base reaction. And this is the reaction whose equilibrium constant is the Kb that we are talking about up here. So with this having been written down now, what do you think our next step is going to be? The chat says an ice table, and that's correct. We have an equilibrium, we have an equilibrium constant, and we have an initial concentration. So that seems to point in the direction of an ice table. Okay, we have found our initial concentration of the base. I'm going to write that as 5.495 times 10 to the minus 10 to the minus 3. What do we put over here? What's our initial concentration of the BH plus? The chat says 0. That's right, because we didn't put any of that in. Hydroxide ion concentration. In pure water, what is our hydroxide concentration? What is the pH of pure water? Yes? 7. What is the pOH of pure water? 7. That's right. So if the pOH is 7, what is the initial hydroxide concentration? How do you go from pH to, pOH to concentration? We know that we can do this to go the other, well, actually, no, this is actually it exactly right here. So if the pOH is 7, our hydroxide ion concentration is 10 to the minus 7. Now, it may end up being that that ends up being negligible and we can ignore it. We'll make that decision in a moment. So we have our initial line for our ice table. What does our change line look like? Which direction is the reaction going to shift? There's only one direction it can shift. The chat says to the right, and that's correct. Why is that the only direction it can shift? What would go wrong if we tried to say it was going to the left? The chat says we would get a negative concentration. That's right. If this reaction shifted to the left, we would be taking away from the BH plus concentration, which starts at 0, and so it would go negative. So it can't do that. So if we are shifting to the right, minus x, x, x. And we have 5.495 times 10 to the minus 3 minus x, x, and 10 to the minus 7 plus x. Okay. So we now take a look at our equilibrium constant, which we are told is 3.2 times 10 to the minus 6. So our equilibrium constant, 3.2 times 10 to the minus 6. And what is our expression for the equilibrium constant? What concentrations do we put into this? Let's start with the numerator. What's going to go in the numerator? Yes. So the BH plus, and what else? The hydroxide. What goes in the denominator? Yes? B and H2O2? Well, the B goes in the numerator, but there is a reason why I crossed out the H2O column. What is the reason I crossed out the H2O column? Yes? Right. Yeah, it's a liquid, and so its concentration is effectively constant over the whole course of the reaction, and so it isn't a concentration that changes, and so we fold it in to the equilibrium constant. Okay, so now we plug in our values for this. We can do 5.495 times 10 to the minus 3 minus x. Oops, that's the denominator. We have x times, and we have to make a decision here if we're going to call it 10 to the minus 7 plus x, or if we're just going to call it x. And that's going to depend on how big we think x is. If we think x is going to be really small, then we can ignore the x here. If we think x is going to be really big, we can ignore the 10 to the minus 7 here. If we, I'm sorry, if we, you're right. If we don't know, and in this case, 10 to the minus 6 is not, it's small, but it's not ridiculously small, we might want to go ahead and keep it in. And in this case, we still only end up getting a quadratic equation at the end, so that's probably okay to work with. So we multiply through 3.2 times 10 to the minus 6th times 5.495 times 10 to the minus 3rd minus 3.2 times 10 to the minus 6th times x equals, I'm going to plug that through, 10 to the minus 7 x plus x squared. Okay, let's bring everything over to the side where the x squared is positive. So we have x squared. We have 10 to the minus 7 x plus 3.2 times 10 to the minus 6 x minus, I'll go ahead and figure out what this one is, 3.2 times 10 to the minus 6 times 5.495 times 10 to the minus 3 gives us 1.75, call it 76 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8. 10 to the minus 8 equals 0. These two can combine. So x squared plus 10 to the minus 7 is going to be in that decimal place right here. So it's going to then be 3.3 times 10 to the minus 6x minus 1.76 times 10 to the minus 8. And we want to know what our roots of the equation are. What I generally do in this case, because I hate having to do the arithmetic for the quadratic formula, is I look up a quadratic formula calculator. I just Google it. The first one that comes up is from a place called Calculator Soup, and that one seems to work well. So I put in the coefficient of A is 1, coefficient B is 3.3 times 10 to the minus 6, and coefficient C is negative 1.76 times 10 to the minus 8. We get two roots. One of them is negative, one of them is positive. Only the positive one can be correct because we can't have a negative concentration in this case. And so our solution is that x equals 0.000131. Now we have to look back at our ice table and see which of these is the concentration we need to worry about. It's the hydroxide that we're looking for. So the correct answer is 10 to the minus 7 plus x. This is 1, 2, 3, 4, 5, 6. So the seventh digit's going to be out here. So we don't even need to worry about the 10 to the minus 7 part at this point. And so now we know that this is our concentration of OH minus. The question is asking us for the pH. What do we do next to find the pH from a concentration of hydroxide? Yes?
I'm kind of confused. So you just ignore the 10 to the negative 7.
Because if we took this number and added 10 to the negative 7 to it, it would be adding a digit down here that's past the digits we're considering significant. And I'm only keeping 3 significant digits here. I probably actually should only keep 2 significant digits because KB is given to us with only 2 digits. But I kept an extra one just out of safety. So for that part of the calculation, it doesn't matter. That's right. Okay, so we have a concentration of OH. How do we get from that to a pH? There are 2 different routes you could go. A student on Piazza posted this little diagram that shows a bunch of conversions you can do in an aqueous system. Going from H plus concentration to OH minus concentration, converting to the P scales, and then comparing the pH and the POH. These relationships need to become second nature to you because they are extremely common, very rapid. Very, very common. You need to not be slowed down having to think about what's going on. This relationship up here at the top comes from the fact that Kw, the auto dissociation of water, is the hydronium ion concentration times the hydroxide ion concentration, and you just solve it for which one you're trying to get to. And remember, Kw at 25 degrees C is 10 to the minus 14. This relationship down here comes from the fact that when you take the negative log base 10 of 10 to the minus 14, you get 14. So the sum of pH and POH always equals 14. And both of these conversions from a concentration to the P scale uses the fact that P of whatever equals the negative log base 10 of that whatever. And simply solving this for the other quantity here, for this side, the individual component equals 10 to the minus P of that component. So in that box, you can put H for the pH, you can put an OH for POH, You can put a Ka or a Kb for the equilibrium constants for the acid or base reactions. This same set of relationships is true for all of them. Okay, so given this information, and given that we have a concentration for OH, what are the two different ways that we could calculate the pH of the solution? Chat answers. It says negative log of concentration of OH. That would take us from here to here. Then we will have our POH. How do we get from that to pH? We subtract it from 14 across this way. The other way we could do it, instead of going this way around the box, you can go this way around the box. So you can take your hydroxide ion concentration, you can take 10 to the 14 divided by that to get the H plus concentration. And then you take the negative log of this to get to pH. Those are mathematically equivalent approaches. Nothing makes one of those better or worse than the other. Okay, so if we do that for this particular value, I'm going to go this way. So I'm going to take the negative log base 10 of 0.000131. I'm going to take the log base 10 of that, change sign, and we find that our POH equals 3.88, which means that our pH equals 14 minus this, or 10.12. Okay. Okay, any questions on any of the steps in solving this kind of problem? Okay. All right. Oh, that was a holdover from yesterday. We didn't have any questions on autoionization water. Percent ionization. How do you calculate the percent ionization? And the specific request was to have an example that has to do with bases. So the very first thing you do is you write down the standard base reaction like this. The percent ionization is the amount of the base that is in the ionized form over here. So if you take your initial base concentration, which is going to equal your current base concentration plus your current BH plus concentration, because for every molecule of base that converts from this to this, you get one. You subtract one here and you add one here. So the total amount of base that you have, put that in the denominator. And in the numerator, you put how much of it has gone into the ionized form. That is our fraction that is ionized, multiplied by 100% to turn it into a percent, and that's all you do. So in this particular case here, we determined that X was 0.000131, which equals our concentration of hydroxide, but it also equals the concentration of BH+. So we can find our percent ionization by taking 0.000131 divided by the concentration we started with, 5.495 times 10 to the minus 3, and we find 0.000131 divided by 5.495 times 10 to the minus 3, we find that we get a fraction of 0.024. So multiply that by 100%, it's 2.4% ionized. Any questions on percent ionization? Okay. All right. So there was some conversation about, there were some questions about amphiprotic substances. And I've discovered that apparently the textbook and the Newton homeworks are making a distinction between amphiprotic and amphoteric. So let me make sure that that distinction is clear. Amphiprotic means that it is a substance that can act as either a Bronsted-Lowry acid or a Bronsted-Lowry base, depending upon what context you're talking about, which reaction you're talking about. Amphoteric is a broader definition which says that it is a substance that can act as an acid or as a base by any definition of acid or base. And so that includes amphiprotic substances, but it will also include substances that could be either a Lewis acid or a Lewis base, but doesn't involve a proton transfer that's involved. So in this class, we are primarily focusing on Bronsted-Lowry. And so unless I specifically say Lewis acid or Lewis base, then when I say acid or base, I'm talking about Bronsted-Lowry. Because of habit, I tend to say amphoteric. But because we are primarily focusing on Bronsted-Lowry, what I generally mean when I say that is amphiprotic. So if there is ever a case where you need to be thinking about amphoteric in terms of a Lewis acid-based situation, I would specifically say it was a Lewis acid-based situation. I can't imagine that that is something I would be testing you guys on, though, simply because for Gen Chem kinds of concepts, the Lewis acid-base topics aren't as important as the Bronsted-Lowry topics. You will find much more going on about Lewis acid-base topics once you get to organic chemistry. So let's look at some examples here. Which of the following is not amphiprotic? And so this actually ties into a different question, which comes up later, dealing with Bronsted-Lowry acids and bases. How do we know if an acid is weak or strong? And so the question then is, can we just look at the chemical formula and determine if it is weak or strong? There are quite a few strong acids. There are quite a few strong bases, but the numbers of them that are commonly found is actually pretty short. There are really only about 6 of each. And so this is a list that you probably want to have. So we have a list here of the 6 common strong acids and a list of the 6 common strong bases. And so here at the Gen Chem level, unless you are told specifically that an acid or a base is a strong acid or base, you look at this list. And if it's on this list, it's a strong component, acid or base. If it's not on the list, you assume that it is weak. Okay. Now, one of these common strong acids you notice here is labeled as diprotic. This last one, H2SO4, is diprotic. That is because both of the hydrogens on sulfuric acid are strong acid protons. So you put sulfuric acid into water, it will deprotonate both times to leave the sulfate ion and two of the hydronium ions as a result. So with that in mind, let's look back at this question about which of these substances is not amphiprotic. And we notice here that H2SO4 is one of the species that is listed. So we know that it's a strong acid. Sulfuric acid is a strong acid. It's a strong acid with both of its protons. And so this is not something that is going to accept another proton. So this cannot act as a base. So this is the one. Ammonia, we have seen it act as a base in accepting a proton from water to make the ammonium ion and hydroxide ions. But it also can donate a hydrogen to make NH2 minus. H2PO4 minus, this is a dihydrogen phosphate, which is one proton removed from phosphoric acid, which is H3PO4. All three of the protons on phosphoric acid are acids. So you can go all the way from H3PO4 all the way down to PO4 3 minus, losing a proton at each step. But all three of those are weak acid steps. And so this can gain a proton acting like a base to make H3PO4. It can donate a proton to give HPO4 2 minus. And HS minus, this one can accept a proton to make H2S, hydrogen disulfide, and it can lose a proton to make the sulfide ion S minus. So I think you probably have seen some of these ions that it forms in Chem 111's material when they were talking about, I think there was a section on ionic compounds and maybe even solubility rules. Were those talked about in Chem 111? So a lot of these ions, like the H2PO4 minus and the sulfide ion and such, were part of that, that list. So of these, because we know that H2SO4 is a strong acid for both protons, we know that it's not going to accept another proton, and so this has to be the amphoteric one. Now, another question was brought up, is there a list of amphoteric substances? And the answer is no, simply because there are certain functional groups on organic compounds that can act as a either an acid or as a base. So we've looked at acetic acid, for example, which has a structure that looks sort of like this. We've looked at something similar to ammonia here, where there's an but one of them is attached to a carbon instead to a hydrogen. So we would expect that this part can act like a base. We expect that this part can act like an acid. And then we can attach anything off of this carbon that we want to. We could put all kinds of things to make literally thousands to millions to maybe even billions of different kinds of compounds, where the molecule as a whole will have one region that acts as an acid and another region that acts as a base. So this is the kind of thing that you will start learning more about in organic chemistry. So we're not going to go into too much detail here, but the upshot of this kind of thinking is that there isn't a simple list of amphiprotic substances, simply because that list would just be ridiculously long. Okay, any questions on amphiprotic, amphoteric substances? Okay. All right. So there was a question about Bronsted-Lowry acids. When given an equation like this, how do you determine which substance is acting as an acid when the reaction proceeds in the forward direction? So, and this is specifically in the context of Bronsted-Lowry. So for this, you just have to go back to the definitions. A Bronsted-Lowry acid is a proton donor. So if we look at what's happening here, what do we have on the left-hand side that when it shows up on the right-hand side is missing a proton from it? Okay. And so it looks like it's the fluorine. The HF becomes F minus, so we have lost an H plus. So this is the acid. This has to be the base because it is accepting the proton from the hydrogen to make this. If we look at the reverse reaction, the H3O plus is donating the proton back to the fluoride. So this is the acid, this is the base. And so this acid-base pair is a conjugate pair. This acid-base pair is a conjugate pair. Okay. Any other questions on Bronsted-Lowry acids and bases and how to identify what's acting as what? Yes. Sure. So explaining what conjugates mean, what a conjugate base and a conjugate acid means. So the idea is that for any acid-base reaction, so if we have HA plus B in equilibrium with A minus plus HB plus, okay? We see that the A is kind of the carrier here, and it either exists in the state with the proton on it or not. We see that B is the same kind of thing. It exists in either the state with the proton on it or not. So that pair is a conjugate pair. Okay. When you identify that on one side, this pair acts as an acid, then on the other side, it is acting as a base. Because over here, it has already given up its proton, and so to go back, it will have to accept one acting as a base. And the same argument here. If this is acting as a base on this side, then for the reverse reaction, its conjugate is acting as the acid. Okay. Now, we talked about how there is a standard base reaction, which we wrote down earlier. It's something like B plus H2O is in equilibrium with BH plus OH minus. And we said that this standard base reaction has an equilibrium constant we call Kb. Well, for a standard acid, HA, we have a standard acid reaction as well, where we react it with water to form A minus plus H3O plus. And this reaction has an equilibrium constant we call Ka. There is a relation, if this and this are the same, so that B and HA here are conjugates of each other. Okay, so if B and HA are conjugates, then there's a relationship between Ka and Kb. Ka times Kb equals Kw. Okay. So where does this come into play? Why do we care about this? Well, let's look at an example of acetic acid. So CH3COOH. This is the acid that is in vinegar, and we know that if we put it into water, it will have an equilibrium with the acetate ion and the hydronium ion with some Ka equilibrium constant. Well, we also can make a compound, an ionic compound, that is a salt of the acetate ion. So something like sodium acetate. And so we dissolve that into water to make Na plus CH3COO minus. But if we look up here, we can see that if we put CH3COO minus into water, it's going to have an equilibrium. So if we put CH3COO minus into water and allow it to react with water, it can undergo an equilibrium to make the water basic. So, and we can think of that another way. If we put the acetate ion into water, there's already some hydronium ion present because of the autodissociation of water. But then if we don't start with any of this, the equilibrium is going to shift to the left, reducing the amount of acid that's present. And so the solution is going to become basic. So the convenient thing is that we can look up the Ka for acetic acid, and we can use this relationship here to find the Kb for the acetate ion, because it's just going to be Kw over the Ka for the acetate ion. And so now we know what's going to happen to the pH of a solution if we dissolve sodium acetate into the solution. So that's where the importance of identifying conjugate acid-base pairs comes into play, is being able to recognize, that ion that I'm looking at looks like a deprotonated form of an acid I've seen before. So if I just put that into solution, it's probably going to make the thing basic. Does that make some sense? Okay. Any questions on that, on conjugates in general? Okay. All right. So did that. So apparently there is some kind of question on Newton that was comparing the Lewis model to the Bronsted-Lowry model, and the answer made the claim that the Lewis model is a broader model than the Bronsted-Lowry model. And so the question was, what does that mean? Why in what sense is the Lewis model broader? The sense that it's broader is that almost every, not 100% every, but very, very much most of the Bronsted-Lowry acid-base reactions are also classified as a Lewis acid-base reaction, because what we have is some kind of acid covalently bonded to a hydrogen. We have some kind of species B that is a base, and we have electrons somewhere on here. It might be a lone pair, it might be coming from a double bond or something like that. There are multiple different ways that could work. But we end up having the reaction go to A with those electrons on it, and then H now bonded to B. I'm not tracking charge in this diagram right now. And so very, very nearly any time that you have a proton transfer from one substance to another substance, you will end up with a Lewis acid-base reaction happening as well, because there is an electron pair that is donating to that hydrogen, and the hydrogen is accepting it to form this new covalent bond that is the hallmark of a Lewis acid-base reaction. But the Lewis acid-base reaction can also explain things in addition to this. So a Lewis acid-base reaction could explain a base coming in here to make that. So we can have the electron pair donation to the carbon. The carbon is accepting an electron pair from it, and we form a bond in between them. This is a Lewis acid-base reaction, but it's definitely not a Bronsted-Lowry acid-base reaction because there's no proton transfer going on here. So that is the sense in which the Lewis model is broader than the Bronsted-Lowry model, because the Lewis model is applicable to a much wider range of reactions than the Bronsted-Lowry model is. So another term that is used in Newtonist, I believe, is a coordinate complex, which is what the result of a Lewis acid-base reaction is. And the hallmarks of a coordinate complex is that a covalent bond has been formed where both electrons in the bond come from the same species. So if we have A, B, those electrons come over here and you form A, B, this is a coordinate complex. If, on the other hand, you have A, B, and one electron comes from each source to form A, B, this is not a coordinate complex. So this is a Lewis acid-base reaction, this is not. And so the question is, how do you determine whether you have a coordinate complex? The answer to that is you have to know what the reactants are and you have to know what the products are. So you have to draw out the Lewis structures and count electrons and figure out where did the electrons come from in that bond. So if we said H3O plus F minus yields H2O plus HF, to figure out whether we have a coordinate complex or not, we need to draw out our Lewis structures. And we see here that the fluorine started with 8 electrons in its valence shell. And the entire molecule that we ended up forming here has 6 electrons that are lone pairs on the fluorine and 2 more electrons that are in the bond. So those 2 electrons had to both come from the fluorine ion, the fluoride ion that you started with. So this would be an example of a coordinate complex that is formed by a Lewis acid-base reaction. But you can't really tell that without drawing the Lewis structures. So that's all of the muddiest points that I had. There was one muddiest point from yesterday that might be worth going over today, since I know a lot of people don't cross over and watch the other ones. And this was getting at the question of pH changing with temperature. Is that something people would be interested in talking about a bit? Okay. So the idea here is that for pure water, we have the equilibrium 2H2O. It's an equilibrium with H3O plus OH minus. we said that the equilibrium constant for this autodissociation reaction has a special name, Kw, for K of water, which has the value at 25 degrees C of 10 to the minus 14 molarity squared. And this is the fact that tells us that our H3O plus and OH minus concentrations at room temperature are each going to be 10 to the minus 7 molar, which tells us that our pH and our pOH for neutral water will both equal 7. Okay. It all comes from this fact right here. But this is at a specific temperature. And as we've talked about, the equilibrium constant will change with temperature. So let's see how much it changes in the case of this autodissociation of water. Now, I'm sure this is hard to see, so I will write in the some of the values we're talking about. So here we have 25 degrees C. We have the equilibrium constant is 1.008 times 10 to the minus 14, pH of 7, pOH of 7. Now let's go just 5 degrees away to 30 degrees. We get 1.471 times 10 to the minus 14, a pH of 6.92, and a pOH of 6.92. If we go colder to 20 degrees, we have an equilibrium constant of 0.681 times 10 to the minus 14. These are experimental values. We have a pH of 7.08 and a pOH of 7.08. So the stoichiometry of the reaction doesn't change. So our pH and our pOH in neutral water are always going to be equal to each other. But 7 being neutral is only true at 25 degrees. Okay. So how far does it change? When we get down to 0 degrees, we're looking at neutral pH of 7.47. At 100 degrees, we have a neutral pH and pOH of 6.14. So that's the range that we have to work with for pH and pOH of neutral water within the liquid range of water. So with this in mind, the little box notation that I showed you here, that screws up this number here and this number here. These conversions are the same. It's because the pH and pOH are just another way to represent a concentration. But the relationship between pH and pOH as a constant value, or between hydronium and hydroxide ion concentrations, that value changes with temperature. For the most part, in a Gen Chem class, we will be focusing on 25 degrees C just to make things simple. However, when you go on to biochemistry, for example, you will find a lot of cases where you're dealing with body temperature, or if you go into medicine or something like this. And so the body temperature is not 25 degrees, it's 37 something, I think, degrees C. And so the neutral pH and pOH are going to be slightly different from the 7 that we're used to. Any questions? We have about 3 more minutes if anybody has anything you'd like to talk about. Yes?
About like the content, but how would you study for the test?
How would I study for the tests? So the first thing I would do is try to think about think about the reasoning steps that are behind pieces of information. So, for example, here, if you have this box tells you how to get from any of these pieces of information to any other piece of information. But you could construct something similar anytime you have an equilibrium going on, right? And so maybe taking a step back and saying, okay, what if this were a different equilibrium? What if this were an equilibrium for ammonia disproportionating into NH2 minus and NH4 plus, rather than water dissociating into H3O plus and OH minus. And then if you can think through how, why is the connection here 10 to the negative 14? Oh, well, it's the equilibrium constant. Okay, so if I know the equilibrium constant for NH4 plus versus NH2 minus, I could do a similar thing here. So it's not necessarily that I'm going to throw that kind of question at you, but that kind of thinking so that you understand not just, well, I know I use 10 to the minus 14. Knowing why you use 10 to the minus 14, that's the kind of thinking that will help you in thinking through test type questions. And so studying for the test would be, what are the connections that have been made? Do I understand why those connections are being made that way? That's kind of what I would try to focus on.
So would you like go through like the content videos and come up with like, watch them and kind of like pause them and kind of just like think it over?
Absolutely, and I would, so watching a content video and then I make a statement of something in it, and then stopping and thinking, okay, where did that statement come from? It's not just a piece of data I'm giving you in most cases. It's usually a chain of reasoning that explains why we do something the way we do. And so thinking, okay, can I reproduce why Osman made this statement? You know, that is, I think, one of the best things that you could do. When there is a sort of a procedure to follow, then making sure you're comfortable with that procedure. So on the last exam, for example, the middle third was about mechanisms. And in class, we went over quite a few examples of different kinds of mechanisms, doing the steady state approximation, doing pre-equilibrium approximation. And so, and there were standard steps that we went through that were part of that, taking an elementary reaction and being able to write down what its rate law is very quickly and efficiently. Okay, so making sure that you're quick and efficient at doing that for the things that don't really require a lot of thought to do, so that you can spend your time and energy on the things that do require some thought. And so then pre-equilibrium approximation, what is it? What is the fundamental concept of the pre-equilibrium approximation? Well, it's an equilibrium, and so that means the forward rate equals the reverse rate in a reversible reaction. And so then knowing, so not just I see the equilibrium lines and I know to make those rates equal, but if it's written in a different way so that the forward reaction's here, the reverse reaction is written here instead of being written that way, knowing that well, it's still the reverse reaction, so I make those rates equal for pre-equilibrium. So essentially just thinking through the steps in the development of the ideas so that you see the connections. Because, you know, when somebody posted this, for example, I looked at it and thought, no, that's not very useful, because you can reconstruct any pathway here by understanding what a p-scale is and understanding what the relationship between pH and pOH is and what the relationship between the concentrations are in an equilibrium constant. But then I realized, wait a minute, that's the fact that I look at that and say, you don't need this, that may be off, This may help you connect in your own mind that there are connections between different parts of the information, and seeing it in this format may help you make those connections. So, but that's the ultimate thing, is making those connections. So, so the goal would be, I think, to have this to make those connections, and then get yourself to the point that you can move beyond it and you don't need to use it anymore. A great example of this, this idea, is something I saw back about 10, 15 years ago. Chemistry textbooks used to make these huge flowcharts where you have mass of reactant, and then you have moles of reactant, and then you have mass, or maybe you have concentration of reactant with plus the volume, which can also lead you here. And then you can go from moles of reactant to moles of product. And then you can go from that to a concentration or volume, or to a mass, and so on. And so it was basically these flow charts that take you through dimensional analysis and stoichiometry to say, in the course of a reaction, if I'm given this and I need this, I can go through these steps to get there. And in some of these textbooks, this kind of diagram would span 2 pages with lots of different arrows and things going in. And it's great from the perspective of, okay, if I have no idea what I'm doing, I'll figure out what I am and I'll just follow the steps to get to the end. But the issue is that each of these steps that you have here is a concept. Here, this is the definition of a concentration. What do we mean by it? This one is molar mass. This one is reaction stoichiometry, and so on. But once I started seeing these flowcharts expand into, multiple pages to try to do something, it struck me that, thinking about it in these terms of a series of steps to follow is the wrong way to go about it. The right way to go about it is to say, I've got a set of tools in my toolbox. I know how to go from mass to moles. I know how to go from reactants to products if I'm in moles. And then once you then get a new concept, then that's just a new tool in your toolbox. You don't have to explicitly say where it's going to fit into the flowchart. So trying to think about this content from the perspective of having those tools and then putting them together in whatever order is necessary to get from where from the information you're given to what the question's asking for. That's the kind of construction that I think is the most useful. Does that make some sense? A little bit? Okay. All right. I went over time. I apologize for that. Thank you all. And remember, my office hours tomorrow are canceled. So if you need to talk to me tomorrow, please do send me a message and we will set something.